Welcome to The Explainer. Today, we're talking about a real powerhouse duo in machine learning, principal component analysis and the support vector machine. We're going to look at how they team up to take a giant, tangled mess of data and turn it into clean, sharp, accurate predictions. So let's dive in.
First things first, I want to kick things off with a question that, it might seem like it has a super obvious answer. Is more data always better? I mean, you'd think that giving your model more features, more columns, more information to work with, well, that can only be a good thing, right? Turns out, in the world of machine learning, more can often be much, much less. In fact, when we keep piling on features or what we call dimensions to our data, we can run smack into a huge problem. And it has a really cool name, the curse of dimensionality.
I know, it sounds totally backwards, but it's a real thing. It's a situation where your model essentially gets lost in the static. As you add more and more features, the actual signal you're trying to find gets buried, and the model just can't figure out what it's supposed to be learning.
And believe me, this isn't just some abstract theoretical headache. The curse of dimensionality has very real, very frustrating consequences. Your models take way longer to train, they hog memory and processing power, and, here's the most dangerous part, they become way more likely to overfit. That means they end up memorizing the noise in your training data instead of learning the actual pattern you care about. So, how in the world do we fight back against this curse? Well, say hello to our first tool in the arsenal. It's a brilliant technique for simplification called principal component analysis, or just PCA. PCA is what we call an unsupervised technique. All that means is it doesn't need labeled data to do its job. It just looks at the data's internal structure and figures out which directions show the most variation, or the most spread. You can think of it like it's creating a highlight reel of your dataset. It keeps only the most important action-packed moments and just cuts out all the boring filler.
So how does it make this highlight reel? Well, essentially, PCA studies how all the different features in your data move together. It then creates these brand new, combined features, we call them principal components, that capture the most important patterns. The first component grabs the biggest pattern, the second one grabs the next biggest, and so on. This lets us build a really powerful summary with just a handful of these key components.
Okay, so PCA has cleaned up our data, simplified it. Now we need a powerful classifier to actually make decisions with it. And that's where our second tool comes into play, the support vector machine, or SVM. Now, an SVM is a supervised learning model. That means it learns from data that's already been sorted into categories. And its goal? It's pretty straightforward. Draw a line, or if you have more dimensions, a hyperplane that creates the absolute clear separation possible between the different classes in your data.
This slide just nails the core idea perfectly. An SVM isn't looking for just any old line that separates the data. No, it's searching for the one specific line that creates the widest possible street, or margin, between the two groups. And that wide margin is what makes the classifier so much more confident and reliable when it sees new data for the first time.
So what's the secret sauce? What's the engine that's driving this whole margin maximizing thing? It's a really clever mathematical function called hinge loss. What it does is penalize not only the points that are on the wrong side of the line, but also the points that are on the right side, but are just a little too close for comfort, the ones that are inside that margin. It's a really smart way to enforce that wide separation. Okay, so we've got PCA, our data simplifier, and we've got SVM, our expert classifier. I think you can probably see where this is going. When you put these two together, yeah, something really special happens.
The synergy here is just brilliant. PCA acts like a noise filter. It cleans up the data, gets rid of all the distracting clutter, and then hands this much simpler focused dataset over to the SVM. With all that noise gone, the SVM can do its job so much better, finding a really clear, robust decision boundary with way less computational heavy lifting.
And this isn't just a nice idea in theory. The results absolutely speak for themselves. A 2021 study put this PC-SVM hybrid model to the test on the really complex task of predicting software bugs. And I mean, just look at the accuracy scores on these two NASA datasets. They are incredibly strong, even hitting over 95% on the CM1 dataset. That's fantastic.
All right, listen up, because this is probably the most important part of this whole explainer. Using these tools together is incredibly powerful, but if you do it in the wrong order, all of your results will be completely and totally meaningless. There is one golden rule you absolutely cannot break: no peeking.
This brings us to the crucial question. It's the exact kind of practical detail that someone on Stack Overflow asked about, and it's the kind of thing that can make or break an entire machine learning project. So, do you apply PCA to your whole dataset and then split it into training and testing, or do you split it first? Okay, here it is, plain and simple. You have to split your data into training and testing sets before you do anything else. The right way, as you see here, is to use only your training data to figure out those principal components. Then, you apply that exact same transformation to both your training data and your test data. So, why is this so critical? Well, as the user Shortwave Dave perfectly put it on Stack Overflow, the test set is sacred. It's supposed to simulate brand new unseen data. If you fit PCA on the whole combined dataset, your model gets a little sneak peek at the test data while it's learning. That's like letting a student see the final exam questions while they're studying for the class.
This huge mistake actually has a name. It's called data leakage. It happens anytime information from your test set accidentally leaks into your training process. And what happens is you get a model that looks absolutely amazing during testing, but then it completely fails in the real world because its performance was totally artificially inflated. It basically cheated.
So we know how powerful this PCA and SVM combo can be, and we know the right way to put it together. But like pretty much everything in machine learning, this powerful technique comes with a trade-off. On the one hand, you get these huge benefits. Your model gets way more efficient, it often gets more accurate because it's focused on the real signal, and it's less likely to overfit. But, on the other hand, you are throwing some information away. And because those principal components are these abstract, mathematical combinations of your original features, they can be a lot harder to interpret in a simple, real-world sense.
And that really leaves us with a final, big-picture thought. It's the central question that pretty much every data scientist has to wrestle with on every project. You have to decide if that trade-off is worth it for your specific problem. So when is sacrificing a little bit of detail, a little bit of nuance, worth gaining a model that's faster, simpler, and ultimately a lot more accurate? Well, that's the art of it, isn't it?